All right, welcome to the third session. Technically, the screen says second session. This is because we couldn't complete what was meant for the second session, and I didn't want to redesign the UI. So, yes, sorry for that. So, we're basically going to continue the third session with the second session, sorry. Although the third session we were supposed to be talking about something else, but we couldn't finish. So, just forgive me on that. All right. So in the previous sessions, we started talking about charges. We started talking about potential energy, voltage. What do we mean when we say that potential energy per unit charge? What voltages? We talked about all these things. Okay, and then we got to the point where we're looking at formation of potential differences. Okay, and I said something. The first thing was that for energy to flow, we made things clearer that for energy to flow there has to be some form of potential difference, right? It is just a situation like you have water, a river that is flat, okay, no gradient. That river will stay static, probably to be called a lake, right? But then for the river to flow, there should be some form of gradients so that it will be acted on by gravitational potential energy to move downstream, right? Great. The same way for for charges, we don't need gravitational potential energy because the force that works in this domain is not gravity, but it's what we call the Coulomb law, and then Coulomb force. Sorry, and we also describe that Coulomb force. Um, First of all, it's one of the strong forces of nature. Okay, and it's actually very strong compared to gravity. Coulomb force is way stronger. So Coulomb force could actually exist, and there's actually the existence of potential energy so far as we have a configuration of charges if they are moving or not. Okay, great. So we asked the question that we started with formation of potential. We said potential energy is required. We already know what potential energy is. But I said this, that the potential difference that we talked about in the previous session, that we said is the energy that creates the field. Okay, the accumulation of those charges create the field, and the field end up having a potential energy. This has to be sustained. Okay, we have to make sure in our electronic system we have to make sure that this energy is not changing. By the way, this is not something you as the electronic system designer you worry about, because everything has been factored into the design of the batteries, right? However, I need you to understand so that when you are building your systems, you really know why some things are happening. Okay, so that it doesn't become like you are a passive designer. No. Okay, so all these things that I'm talking about, they are what happens in the power sources that we use, like the batteries, like whatever power source you are talking about. Okay, great. So we need to sustain that potential, because the moment the potential is lost, it means that the electric field is going to break down. And once the electric field breaks down, there will be no there will be no force field, right? And all this potential energy will be lost. So if we're going to sustain it, then it means that we need a mechanism to be generating, right? Something. So even if there are losses, they should be replenished, right? Great. So one of the requirements is that these charges have to remain static. We also mentioned that if the charges themselves begin to move, and please take note that we are talking about the charges that is creating the field, the field that has the electric potential, right? They have to remain static, because the moment they begin to move, part of that electric potential energy is going to be converted into kinetic energy, and there will be a reduction. We don't want that. Okay, so we need to make sure that the charges that are creating our potential gradient remain immobile. That means they can't move. So now the question is, how can we achieve this? Okay, great. So we're going to, in the next sessions, we're going to look at these things and then understand how even batteries work. By the end, we will get the understanding of how batteries or power sources work. Okay, so let's take a battery for instance, and for the sake of teaching, I'm going to simplify things. Okay, once again, I'm not gonna go into the chemistry of batteries. I'm just going to treat batteries from the physics point of view. Is that okay? I'm not going to do all those chemical reaction thingy. No, no. All those chemical reactions lead to generation of charges, right? So I'm going to abstract away those details and just work from the point where the charges have been generated. Is that okay? So if we take a battery for instance, and for now this is my simplified battery model, right? This area you have here with the brown circles, that's going to represent my positive charge zone, or the anode. And this so this for now is the positive material, right? It could be any material. So far as that is what ends up being positive, that is what this region represents. This region represents the negative zone, or the cathode. Okay, it could be any material. We don't care about the battery technology. Like I said, we are abstracting the details of the chemistry of the batteries away. So we are only interested in when the charges get generated. So we said earlier that a battery converts chemical energy into electrical through chemical reactions, right? And if you remember how chemical reactions proceed, basically when chemical reactions is happening, one component is losing electrons and another is receiving them. Basically, that's how chemical reactions proceed. Okay. Now, the moment one element or atom loses electrons and another receives it, a bond is established between them. Okay, a bond is established between. This is the same thing that happens between human beings, right? So I have something and you come for that thing. If I didn't gift it to you, then you owe me that, and by reason of the fact that you owe me, we have a connection. Is that okay? The atom that is losing the electron cannot gift the electron to the one receiving. It is basically just giving it to it, borrowing it to that particular element. So they don't just give it away. It's they are lending it. Take it as a player going on a transfer, right? I don't know how the football people say it, but they loan one team loans another team a player, right? The player is just going to do something. When needed, it will come back, right? So the moment the separation happens within this compound, the electron that was sent to or was borrowed will have to come back. Is that okay? Great. So the battery does this by chemical reaction. So during that period, I don't know if you saw the animation. Please look at this side carefully. So as the chemical reaction is proceeding, what happens is that electrons are stripped off from what will end up being our anode to what will end up being our cathode, right? Now, in chemistry, they call this, I think, sometimes an oxidative redox reaction. I've forgotten my chemistry a bit, okay? But what is happening is that the anode undergoes reduction, right? Oxidation, and loses electrons and becomes positively charged. Is that okay? So, after that happens, any atom in the anode material that lost its electron becomes positively charged. Remember, we define positively charged as the absence of an electron. Okay? And at the anode side, there is what we call, I think I made some mistake in here. The anode is supposed to go through reduction. Oh, I'll verify it, okay, but I think something doesn't sound right to me. Okay, okay. So I'll rectify that and I'll cross check and make sure it's right, okay? The cathode material, all the atoms in the cathode material that received the electrons has now gained one electron more than they used to have, right? So that means that each of them has one electron more than protons. So they become negatively charged. Now, this is where I am interested. These atoms that have lost their electrons, they turn into something called ions. Okay? Ions. Now, ions are electrically charged atoms. So we have positively charged ions here called cations and negatively charged ions here called anions. Okay? Now, why am I stressing on this? Why am I stressing on this? Okay? Ions, unlike electrons, do not move. At least ions in solid materials. Remember earlier we said that we need the charges that are creating our potential gradient to remain static. So they cannot just be mere electrons because electrons will move, right? But these ions are deeply embedded into the crystal lattices, so they don't move. The best movement you could probably get would be vibration about a fixed point, okay? But even by so doing, they don't move from one point to another. Please, I hope this is okay, right? So, because what with the charge accumulation here is as a result of ions, and ions do not move, we create static charges. The same way, these materials here that have gained the extra electrons now form negatively charged ions, also called anions, okay? And they are immobile, so they also don't move. Now, the way the battery is engineered is such that these electrons cannot actually go back to their parent atoms through the battery. It has to do so through an externally connected wire. At least, even if it has, that is where it can pass. It can pass back through the battery to neutralize it, okay? So this is what we call charge generation and separation. So every power source, talk of solar panels, whatever it is, has these two processes. Charge has to be first generated and it has to be separated. Okay? The separation is what brings about the potential difference. So ladies and gentlemen, if we ask the question of how do we generate the potential gradient such that the charges there are immobile and can be sustained, this is how it works. So what then, after doing this, what then does the chemical reaction do, right? So the chemical reaction now makes sure that there is charge neutrality between the anode and the cathode, okay? So if for any reason, an electron falls into any of these ions to neutralize it, this chemical reaction has to occur to strip off that electron into the cathode zone. Okay, now take note, if any electron will come back, then that electron definitely came from the cathode, right? So that means for an electron to come back to the anode, it was lost from the cathode. So there will be imbalance. And so the chemical reaction will happen again and make sure that that charge that's returned is stripped back. Now, In our previous knowledge of electronics, I know most of you have this idea of electrons cycling through the battery in a circular form like that. Please, that is not how things happen. Okay? It's not like the electrons are running through the wires going circle, circle. No, that's not what is happening. Okay? That's not what is happening. Now, let's proceed. Okay? So, so far as we have positive charges accumulated here, negative charges accumulated here, what do you think is going to happen? Electric field is going to move around it. So if you take a battery, there are electric fields all around the battery running from the positive to the negative terminals. Okay? Unfortunately, electric fields are not like magnetic field that you can feel a repulsion when you bring two magnets together. Okay, that's why when you bring two batteries together, you don't feel any push. Okay, so if electric fields are moving already around the battery, does that mean the battery would can die off even though you are not using it? No, technically and theoretically, no. You see, for electric energy to be moved, earlier I mentioned that we need both electric field and magnetic field for this to happen. Okay, I think I'll talk about this more as we move. So just the electric field alone is not enough to move energy from the battery. Okay, however, over time batteries do lose their voltage, and that has nothing to do with the fact that it's because the fact that they have electric field. It loses because of imperfections in the materials that have been used. Okay, so occasionally we have leakages happening, causing the chemical reactions to occur, right, at a very slow pace. So if you give it a very long time, this becomes appreciable and it depletes the materials that are being used for the chemical reactions. Okay, but it has nothing to do with the fact that the battery has electric fields around it. Okay, all right. Now, so these ion cores are not mobile. We have already established that fact. These ion cores are not mobile, which is a very important thing for us. Okay. So without any load, yes, as I already mentioned, without any load, the battery is theoretically not supposed to degrade. But then it happens because of the imperfections in the material. Okay, great. Now we're going to perform more thought experiments. I like thought experiment because it's a way to bring out your understanding. Okay. Let me just put around that it just started raining, so my internet may start misbehaving. Okay. Now, assuming we connect two copper wires to the terminals, right? So if we take the anode side, we connect a copper wire, a copper plate, whatever metal. So far as it's copper, we are okay. And we connect another one also at the terminal. What would happen? Okay. Take note that with this experiment, these terminals never touch each other. They are still opened. They are not connected together. Is that okay? So when we do this, what will happen is that the charges that accumulated at the positive side, remember when we put charges on a conductive surface, what happened? It redistributed and made sure that it covered the entire surface. So because this copper is actually a conducting surface, when we connect the copper to the positive side, the positive charges would redistribute over that copper. The same thing is going to happen at the negative side, okay? But then there will be no there will be no change in the charge. There is still going to be charge neutrality. Why am I saying this? You see, this copper that you brought, a copper that we added was electrically neutral. It had equal number of protons and equal number of electrons. Let me put it like this. It has equal number of ion cores and electrons. So it wasn't electrically charged. So was the one that we connected at the anode. So by extending this or adding this copper to the terminals, we don't introduce any charges, okay? What is going to happen is that we've given the charges that have accumulated at the positive side more room to spread, and they will spread. That is why if I connect wires to the battery terminals and I put a voltmeter between them, I will still measure the voltage of the battery as if there was no wires, there were no wires at all. Is that okay? I need you to really understand these things. So nothing would happen, the charge will just redistribute themselves, okay? And then they will spread over the entire copper surfaces. Great, let's continue. Now, so far as this connectors or terminals or wires that we have attached to the terminals remain open, the charges only redistribute themselves, no energy is moved. Now, somebody may ask that, okay, so if I put a very long copper wire here and the charges redistribute, is that not going to spend some of the energy? The answer is no. Okay, the answer is no. Now, no, because remember we said that for energy to move, there has to be a potential gradient. For energy to move, there has to be a potential gradient. If I connect a piece of wire to this terminal, they are all connected to the same gradient, the same voltage or energy or potential. That means there is no gradient. So the charge will just redistribute as a result of the Coulombic repulsion or the repulsion due to Coulomb force. But that does not affect, okay, or that does not use up the energy of the battery. Okay, now a surface that is at the same potential at every point is called an equipotential surface. Okay, so if we say that something is an equipotential surface, it means that the voltage at any point is the same. So basically what we get here at the anode and what we get here at the cathode are equipotential surfaces, and charges do not spend energy moving on equipotential surface because there is no potential gradient. Great. Now, we keep saying this. For energy to move, there has to be what? A potential gradient. So far as there is no potential gradient, no energy would be lost. Now, the second scenario, this time, we are going to connect a simple light bulb between the terminals. We are assuming that the light bulb's energy requirement matches the battery, right? So the light bulb is rated whatever voltage this battery is rated. Is that okay? So what happens when a load such as light bulb is connected between the terminals? Okay, so the first important thing is that now the circuit has been closed. Anytime a circuit is closed, energy now has the ability to flow. Anytime circuit is closed, energy has the ability to flow. Is that okay? So the circuit closes and the path is created for continuous motion of electrons. Okay? Now, as such, energy begins to move from the battery into the bulb. But the most important thing here is, how does the energy move? Remember in, I think, the second session, I mentioned that the movement of charge is not movement of energy. I mentioned that. Now we will see why what I said is true. Okay, so take note that the energy itself does not travel through the wire. Okay, if I have this setup, the energy, okay, and I know most textbooks, videos on YouTube keep saying, and the electrons, so the people think that the electrons push themselves around, or the electrons gain kinetic energy, move through the wire and release that kinetic energy at the load. No, that is not what is happening. Okay, that is not what is happening. You see, the energy of the electron is not the energy that powers the load. Yes, the electrons do get energy, but that is not the energy that powers our load. Okay, and I'll explain very soon. So take note of that. The energy doesn't flow through the wires. actually the energy flows around the wires, because the energy we are talking about is electromagnetic in nature. It doesn't flow through the wires. Okay, so the energy flows through the spaces around the wires. Basically, the wires just serve as a waveguide, right? It directs the energy where it should pass, but the energy itself doesn't flow through the wire. In fact, the movement of the electrons is a secondary effect, which depends on the fact that the energy is moving. So now the question is, where does the energy move from and how does the energy move? Okay, so first of all, the energy travels in the spaces around the wire. Okay, the spaces, and the energy is evident in the work done. Okay, so the electrons in this system, and take note that the electrons that we are talking about are not produced by the batteries. We are talking about two different things here. Yes, electrons do, the battery does generate electrons, but these electrons that the battery is generating is what we are using to sustain our electric field. Okay, that's what we are using to generate the charges at the base and at the anode and at the cathode. Okay, the copper wires that we connected already comes with a lot of electrons within it. Okay, so these electrons in the copper wire, they themselves are pushed or accelerated by the electric field that is generated by this anode and cathode. So the electrons themselves are being moved by a force, and that force is as a result of the electric field that has been established. So take note, it's not as if the battery keeps pumping electrons into the system. That's not what is happening. The battery's electron is supposed to be used to sustain the electric field. So anytime a reaction has to happen for electrons to be released, it is because there has been a change in the field charges configuration, and the battery has to quickly replenish it, right? But the electrons that move about, these electrons are already in the conductors. Okay, now in case you doubt this, when we take 1 mole of a substance, according to chemistry, it contains 6.02 times 10 raised to the power 23 number of particles, right? And if we take 1 mole of copper, it will have, each copper atom would have an extra electron in its valence band, right? That means that that 1 mole of copper would have 6.023 times 10 raised to the power 23 extra electrons already in their conduction band. Okay, these electrons, in fact, a fraction of these electrons are what flow to constitute current. Please get this understanding. The way we have painted picture previously, as if the battery is pumping and circulating the electrons through the system, that is not what is happening. Okay, the electrons that are being moved are already in the conductors, in the load that forms the circuit. Okay, now let's continue. So I will give time for questions, and then I will clarify stuff for you in case you have any. Okay, so the flow of energy is evident. Okay, so when energy begins to flow, how do we realize that energy is flowing? Because one, it doesn't make any sound, it doesn't make any light, right? But how do we see that, oh, okay, the circuit is closed and energy is flowing? The flow of the energy causes electrons to move. The flow of the energy causes electrons to move. And take note, the electrons that are moving are not the electrons that are creating our potential gradient. Our potential gradients are ion cores, not just mere electrons. The electrons that are moving are the electrons that are in the copper wire that are being accelerated or pushed around by reason of the electric field that has been generated along the copper wire. Okay, great. So, whenever an electron is moving, a second thing comes into play, which is the magnetic field. Static electrons don't have magnetic field, but moving electrons do have magnetic field. Okay, so anytime electrons begin to move, it changes from electrostatics to what we call electrodynamics. Okay, so you can't analyze moving electrons with the concept of electrostatics. You need electrodynamics principles. Okay, so this image you are seeing here, this is how energy is moving. The energy is propagating through space. The space around the wires, the space between the battery source, the power source, and the load. Okay, all around it like that. The energy flows in the space. The energy does not flow in the battery. The energy flows in the space. The electron, or the energy of the moving charges is not the energy that powers the load. Energy that powers the load is a separate thing. The electrons themselves are moving about because of the energy that is propagated. Please understand this for me, okay? All right. So I think I've stressed that thing a lot, okay? So note that the motion of charges is not the same as the motion of energy. Good point to note. Electrons themselves are moving in response to the flow of energy, I've already mentioned. Okay, so in reality, electrons flow from the negative terminal to the positive terminal. Remember, we said a positive terminal is deficient in electrons, so it has the affinity to pull electrons. Negative terminal has excess electrons, so it has the ability to release. But like I said, one of the things that we need to make sure happens is that the charges that are creating our field get sustained. That means that any electron that is lost, the battery has to react to replace it. Is that okay? So that is what is happening. Now, when the electrons drift in the same direction in response to the flow of energy or the electric field, we call it current. So we've already heard of voltage. Now we've heard of current. Okay, so current is simply electrons that are drifting. Okay, when we say something is drifting, it is not going by its own will, right? The electron would have wished to go somewhere else, but the energy is forcing it. So take it as the energy is pulling it to move in a particular direction that the electron itself is not probably thinking of going, right? So that's what we mean by drifting. Is that okay? So when electrons drift in the same direction, we call it current. Now take note that when we even say 1 amp of current, it is just a few number of electrons. Trust me, compared to the rest of the electrons already in fact, if you should view the system with 1 amp of electron passing through, you may probably not even observe movement. Okay, because the electrons, we describe it as a sea of electrons. Is that okay? So just take it as you are fetching a bucket of water out of the sea. You basically don't change the state of the sea. Okay, so what is happening here in previous understanding, okay, and all this was because of circuit theory. Circuit theory made certain assumptions that most people never looked at those assumptions, okay? And so they went on to learn electronics without understanding the assumptions that were made for circuit theory to hold. We will look at that, so don't worry. Okay, so current therefore is the amount of electrons that flow through a cross-sectional area of a material per unit of time. Okay, so now I've defined voltage, I've defined current. So you know what voltage is, you know what current is. The voltage is the energy. The current is the response to the flow of this energy. Okay. All right. I think I will take questions at this point.